Hello everyone and welcome to another video about acquisition of electrophysiological signals. My name is Marija Novicic and in this exercise I'll show you how to make a simple LabVIEW program for acquisition of electrocardiographic signals and calculating the heart rate of the person. As in our previous exercises, we are going to start from this basic data acquisition application. And at the beginning, we are going to set all of these controls to their correct values. So for physical channels, we are recording for device 1, analog input null, where our output of the ECG amplifier is connected. Sample rate has to be at least 2 times bigger than the maximum frequency in the spectrum of the signal. So ECG signals goes up to 250 Hz, so it is okay to use 250 Hz as our sample rate. Numbers of samples per channel must be smaller than the rate, so we have good acquisition. And in this case, we are going to set that to 10 samples per channel, so that in every iteration of the loop, we have 10 samples to work with. Okay. Now let's go to the block diagram to see what is going on there. So we have these usual blocks for data acquisition with the all inputs that are important connected, and this constant we have to set. So again, we are measuring relative to the ground, so we are going to leave this input terminal configuration as RSA again. And as acquisition sample mode, we are going to leave continuous samples because we want to collect the data all the time the application is running. Okay, so we are going to work today with biomedical toolkit, and I'm going to pin it to my block diagram so I can use the function directly. So this toolkit doesn't work with arrays as inputs, but with waveforms. So we're going to have to change this from array of data to waveform of data. We're going to use this drop-down menu to select analog channel, single channel, multiple samples, but waveform data. And immediately this indicator changes color to signalize the type of the data. I'm going to rename this as ECG data, so we know what are we measuring. I'm going to expand this so everything can fit in this block diagram. And now let's do our project for calculating the heart rate of a person that we connected this amplifier to. First of all, because ECG is a signal with a low amplitude, noise can easily affect it, so we are going to use some filter to remove the noise. First filter we are going to use is notch filter, and it's placed in biosignal measurements folder and then pre-processing folder. We are going to use filtering block, place it on the block diagram, and connect its first input, that is biosignal in, with our ECG data. So we have opportunity to choose between classical filter and notch or comb filter. Because we said we want to use a notch filter, we are going to select that option. I'm going to connect this error, so the error propagates to all blocks, then stop the application. And next thing we need to do is to specify which frequency we want to eliminate. In this case, we want to eliminate the noise from power supply network, and in Serbia that noise is on 50 Hz, so we are going to place constant that is equal to 50. Another input we are going to configure, thing we have to specify, is this DF input, and that is a range from which frequency to which frequency with the 50 Hz in center we are going to eliminate from our frequency spectrum. So the constant here by default is 0.02, but that is too narrow for our needs, so we're going to put that at 0.2 Hertz. So our filter will not get through frequency from 49.8 to 50.2 Hertz. As the output, we get our filtered biosignal. Next filter we're going to use is this high-pass filter, because our signal can be contaminated with breathing actions, and that is a low-frequency noise, so we are going to eliminate these low frequencies with high-pass filter. So we are going to collect our output of notch filter to input of this filter, and the error in and error out. And then we are going to specify design method, create constant, as Kaiser window. We also have to specify the filter type. Is it high pass, low pass, band pass, or whatever? We said we want to use high pass, so we are going to select that. And also we have to say which frequency we want to eliminate. With this content, we specify which frequencies will be eliminated and which will not be eliminated. So this first is going to be set at 3, and this second is going to be set at 0.5. So everything greater than 3 Hertz will not be eliminated. Okay. As the output here, we get this filtered signal. Now, what are we going to do? Because we don't have a lot of samples, mainly we don't have a lot of R peaks in our signals, we are going to collect some of the data a period of time and then perform heart rate detection. So how are we going to do that? We are set the condition as long as this iteration terminal is less than 50. We are going to collect the data, and when it becomes greater than 50, we are going to calculate the heart rate. So why 50? Because in 50th iteration, the 5 seconds will pass, and that is enough time so we can estimate the heart rate of a person. I'm going to put comparison greater or equal than 50, and I'm going to set that here. So if E is greater than 50, we are going to measure heart rate. In other case, we are not going to measure heart rate. So we are putting case structure, in which conditional terminal we're connecting that. And now we can first program the while loop. So what are we going to do? We are going to take this filtered signal into the case structure and take only signal information. So we are going to use waveform components, get waveform components. We need epsilon, and we are going to build array with that epsilon. So we need a build array function, not that one. Build array function, and we are going to add this to array that already is here, but we are not going to build it as 2D matrix, that we are going to concatenate the inputs. So we are going to set that here, and here we are going to use shift register to transfer the data to input of the while loop, and then connect it again to build array. So when this condition becomes true, we are going to have the array of dimension 1250 samples, and then we are going to calculate the heart rate of the subject. So next thing to do is actually calculate this heart rate. So first, because we are going to all we're going to do is shift that window of 1250 samples as the samples arrive. So in each iteration, we are going to take the first 25 samples and put the next 25 samples. So we are going to use the index array, array subset function. We are going to connect our created array, and everything larger than 25 is going to stay, and everything less is going to everything larger than 25th index is going to stay in the array, and everything larger will disappear. And on that array, we are going to add this our epsilon at the moment. So we are going to build array on that. I'm going to set this down here. Okay. And connect this with this. And again, we are not going to make 2D matrix, but concatenate the outputs. And we are going to connect that with our shift register. So now we have the data that is good for next processing. So when we build this array, we are going to build a waveform so we can use another biomedical signal toolkit function. So we are going to use waveform, build waveform. We are going to connect this as the start array waveform and this as data, and at the as the output we are getting the signal. So now we are going to use this function from the ECG folder that is called featured extraction, in which as the output we're getting the whole bunch of features of the signal. So we are connecting this ECG and raw ECG inputs from the same input. That is okay. And in the end, we get this whole features from our signal. So we are going to use this VI that I made. We'll calculate HR. And we are going to connect these calculate features with these features with this feature input. And let's see what is this block doing. So double click to that and let's go to block diagram. So we are taking all of these features and firstly checking if this is an empty array or not. If it is, then we are not going to do nothing. We're going to say the RR interval is 0. And if it is, then we are going to take the R component from this ECG feature array of clusters and subtract it from the previous R component. So why are we doing that? Because we want to see the RR interval between two peaks, time between two peaks, and in that way we are going to get the mean value of heartbeats per minute. So we are going to divide 60 with that array and calculate the mean value. And in the end, we are going to get the number of pulses in 1 minute. Okay, so I'm going to close this. And as the output signal is heart rate. So I'm going to put a constant. I didn't select this. I'm going to put an indicator in our table. Okay, so this RR time, that is our actually heart rate, is going to wait for 5 seconds and then produce the output that is beats per minute. Okay, at the end, the while loop will stop if we press the stop button or if this block produces an error. Okay, in the beginning, we can place the sequence structure, so we can initialize some of our parameters, like ECG data indicator. We are going to create a property node that has property history data and set it to default values, so every time the program runs, it will clear the graphic. Also, we might want to see how our filtered data is looking, so we are going to create another waveform graph indicator, and we are going to say this is ECG data filtered, and also we are going to create a property node to clear the data at the beginning. Clear the graph at the beginning. So we're going to change this to right, no. And we are going to connect this to the same constant. Also, at the beginning, we want this heart rate indicator to be 0, so we don't have any rate. So we're going to set the value of that property node to 0 at the beginning of the program. And now, when we initialize the data correctly and we made all the project, we're going to just set this to look nice. And as the output, we have this heart rate in beats per minute. So let's say the beats per minute. Okay. Also, this amplitude is in volts. And this also. Okay. So that was that for this exercise. See you next time in another exercise.
The previous video presented code programming for the application that could be used for real-time heart rate monitoring. An example of electrocardiogram, ECG, is shown in the figure left. Ventricular systole corresponds to ECG peaks that we call R waves. The time between two R waves is called beat-to-beat interval. Heart rate is equal to the reciprocal value of the beat-to-beat interval. Right figure presents the electrode set up for ECG recording in our demonstration. The first bipolar ECG lead configuration was performed. We have used ECG sensor vernier for amplification and USB 6008 for data acquisition. This video demonstrates the real-time heart rate monitoring of the subject. The left top graphic shows raw ECG signal. You can see a lot of noise because of interference. The left bottom graphic shows notch filtered data. The right graphic shows the estimated heart rate signal. You can see here at the end that the subject became more relaxed, so the heart rate decreased.